Good morning. Here we are once again. It's Physics Video Lecture. Physics 2A Video Lecture 39. So I've got the same goods I had here last time. We'll get to it this time, but first we want to do a couple of homework problems. So I had a request here for problems chapter 10, problems 13 and 14. So homework problems 10, 13, and 10, 14, they were both about thermal expansion. So let's just go ahead and write this out, our formula first of all for thermal expansion. We have, for some object of original length L, then we can say the change in length is equal to the original length, is proportional to the original length. I'll go ahead and write that alpha as the thermal expansion coefficient, original length delta T, and of course that could be L minus L0 equals, we put in the 0 there, alpha L0 T minus T0. Okay. So that's the idea. Now this is the linear expansion. The volume expansion we'll do on the next problem. Okay, linear expansion, and the question was about problem 13, eyeglass frames, blah blah. There's a radius that we want to increase from 2.2 centimeters to 2.21 centimeters. Okay, so we want to go from 2.2 centimeters to 2.21 centimeters, and we're going to increase the temperature above room temperature. So room temperature is 20 degrees, and we want to find the temperature to which we have to heat them. So the first thing we notice, we're going to solve for delta T, because we're looking for the temperature, and that's going to be that delta L over alpha L sub 0. Okay. So the change in length here was from 2.2 to 2.21 centimeters, so it's 0.01, and the original length is going to be, I'm just going to put the alpha here, the original length is the 2.2 centimeters. Okay. So the units cancel, 0.01 divided by 2.2, and then we have this alpha here for whatever the material is. I'll let you guys look that up. And this delta T is now given. Okay. So the delta T is T minus 20 degrees Celsius. So once you find that delta T, then you add 20 degrees Celsius to it, and you have the final temperature to which you have to heat the substance, heat the object. So yeah, best to really start with the basic form, because there's nothing complicated about it. Now the next problem was a volume expansion problem. So we have a steel ball with a certain diameter, okay, and we want to find a temperature change to increase its volume by 1%. Okay. So the volume version, let's stick with this board this time. The volume version of this equation is the delta V, and then there's a beta here, V0 T minus T0. But if you're dealing with a solid, the beta is just equal to 3 times the linear coefficient. Okay? And you can look up the linear coefficient for steel. 3 times that will be the volume coefficient. And again, this is let's go ahead and write it as a delta T, since that's what they asked for. Delta T. So again, we're solving for the delta T. It's the delta V beta V0. So now 1%, you're going to have 1 over this beta, and then 1% will mean that delta V over V0 is 0.01. Okay, 0.01, and that will give you that temperature difference corresponding to that volume difference. Okay, good. So that was from chapter 10, but we are now in chapter 11. I'll go ahead and erase this. And I'll remind us where we left off last time. Kind of the most basic law in thermal physics is the way in which heat flows. So we're talking about heat transfer. And the point is, the heat or the internal energy, the thermal energy, goes from the hotter object to the colder object. So I always like to have this cartoon here, this sketch. So H stands for hot, C stands for cold, hotter to colder, and there's an arrow and Q flows there. We're going to use this diagram a lot because it's a good reminder. Okay? You're not going to reverse this arrow unless you do something special to it. If you just take two objects and put them into contact with each other, the thermal energy goes from the hotter to the colder. And if you wait long enough, the temperatures will equalize, right? If they're in contact with each other, somehow the temperatures will equalize. And there are three mechanisms by which this can happen, through which this can happen. So heat transfer mechanisms. The first one is referred to as conduction. And a couple of examples of this. So I brought my torch. I've got this aluminum rod. And the idea is, if I apply heat right here and wait long enough, my hand's eventually going to get hot. Okay? Because the heat will conduct along this aluminum rod until it gets to my hand here. That's the same thing you get if you put a spoon in a hot liquid. Okay? Eventually the entire spoon gets hot. And so this heat transfer mechanism, conduction, works by, at the atomic level, it works by molecular collisions. There has to be some matter there. Molecular collisions. So that's the heat transfer mechanism of conduction. And there's a nice little cartoon. Of course, for us, all candles are butter candles, right? And so you've got a candle. If you can't draw a torch, you've got a candle, and you have, say, a wire. And then the heat will be transmitted along the wire, and you'll eventually feel it get hot. We had a demo that I don't have with me now, but we had wires of different materials: copper, steel, brass. And we put a little wax plug on each one, and there would be a race to see which wax plug drops off first because it melts. And then you find out that the copper would conduct the heat better than the steel, for instance. Okay. So that's conduction. The interesting aspect here to be mentioned is what we did was we wrapped this thing is warm already. Okay, we wrapped this aluminum rod with paper. And we can roast the paper like a marshmallow without burning it. Okay. That's why it's kind of brown here. And what's happening is the heat is actually just going through the paper into the aluminum rod. If you tear off a little piece of the paper, right, and expose it to the air like I've done here, the slightest flame will ignite the paper, as you see. But if the paper's firmly in contact with the aluminum, it doesn't even burn. It'll scorch. And this I'm telling you in order that, so this is one demo. The second one you guys should do on your own, and that is boiling water in a paper cup. Something that you may not have known you can do. So boil water in a paper cup. And what you do is you put a very thin layer of, because you don't have all day, right? Thin layer of water at the bottom of the paper cup. Candle flame will do the trick. Just like here. You've got your candle flame. And yet be careful, the paper will be charred on the bottom, but if you're careful, it won't burn through and you'll actually get the water to boil. And the point here is that on the layer of the paper cup that's in contact with the water, the temperature is no hotter than 100 degrees Celsius, boiling temperature of water. And the layer's thin, so essentially the paper is never properly heating up in order to burst into flame. So this is a fun one. I recommend you guys try it. And there's an example of heat transfer by conduction. So molecular collisions if you're looking inside of this substance. Now the second mechanism I'm going to first demonstrate. Let me write it down. We have a really good demonstration I forgot all about until I looked at it. So these two objects, this is the machined piece of aluminum and a machined piece of wood. You're gonna have to take my word for it. They've been sitting in a closet like this all day and all night and all year, okay? Which means they actually have the same temperature. But if you feel this one, put it against your cheek, for instance, it feels very cold. This one feels pretty neutral, okay? So that's actually a property of the conductivity. Let's write this down here. Get the number 2 for, we have thermal conductivity. So that's a material property, and it's much higher in metal than it is in wood. So far, so good. You'd have to be here to actually feel these. But you can take a cast iron skillet out of the cupboard that's right next to a wooden handle and grab them both, and you'll actually experience something very similar. So this next demonstration is something you guys can also do. I'm going to bring it up to the camera pretty quickly. So I'm just going to put some ice here on the wood and on the metal, and I don't have to wait too long. But we'll see something in real time. I'm going to bring this up to the camera. See if we can pull this off. Okay. Wish me luck. Okay. Okay, so what you can see is that the ice is melting. In real time, it's melting in the aluminum block. The wooden block, there's nothing going on. The ice is just not melting at all. Aluminum block, we have an instant little puddle of water. Okay. Get a screen capture of that if you want. Okay. So that's an all-time great demo. What you're seeing here, gotta explain that to you. See, the ice on the wood is not melting. There's barely a drop there. Here it's almost completely melted. So that's an example of my cartoon here. So we have this aluminum block with a hole in it, and I've packed some ice on, or put some ice on top. So those are our ice cubes. So which way is the heat flowing? The aluminum block is at room temperature. The ice is, say, 0 degrees Celsius. So the heat is actually flowing from the aluminum block into the ice. So that's our heat flow from the higher temperature to the lower temperature. Anything else? So you guys should try this as well. You may not have an aluminum block, but say you have a cutting board and like I said, a cast iron skillet. So you can do a couple of different objects. You got a cutting board, you've got maybe a plate, ceramic plate, aluminum pot, that type of thing. Just put some ice on each one. Store those objects at room temperature, make sure they're the same temperature. Put some ice on each one and you'll see the same thing that we just demonstrated here. So you've got that thermal conductivity, and I think our book will just call it K. I'm going to call it K right now. And then we'll have a formula that looks something like this. Let's go ahead and sketch an object of area A, thickness L. Okay, so the thickness is L, surface area A, and suppose we have TH on one side and TC on the other. So it's hotter on the left than it's on the right. Then the power, so the Q over T, joules per second, right? So the power of the heat energy that's going through, in other words, the heat energy per unit time that's passing through this object would be proportional to the conductivity, okay, proportional to the area, inversely proportional to the thickness times, T2 minus T1, TH minus TC. I'm just going to write delta T for brevity. Okay. Difference in temperature between those two slides. So there's actually, a formula you can use, and if you're designing systems where you need a certain amount of insulation, you can use a thicker amount of insulation. You make the layer here thicker, then less heat is going to get through. And depending on the substance you have, you can also control the conductivity of it. So we would say a high conductivity is a good conductor, of course, but a low conductivity could be useful as a good insulator. Okay, so the whole issue of thermal insulation is right there along with the issue of thermal conductivity. Good, so that is heat transfer by conduction. Maybe I'll assign one of these problems using this out of the book. We'll see. So this was also that important demonstration. Make a good note of this. This is a fun one. Okay, because it's very surprising to see the difference there. Okay, next, the second heat transfer mechanism. And I'm just going to demonstrate it for starters by holding my hand right next to this flame. It's hot, it's very hot up here. But I can hold my hand right to the side. Really close, you can too, no big deal. Very, very close to the flame. I don't know if you can see the flame, but believe me, it's coming out. Stay away from there. So why can I hold my hand that close to the side of the flame? Okay. It is because there's an enormous amount of heat being transferred by an airflow. So this flame, hot air, is drawing in air and it's blasting out in this direction. So I have an airflow that you can't see, but you know it's there because you can feel it. Whereas on the side, there's just cool air coming in from behind. Okay, and the air is actually a good insulator. So in the absence of the motion of that air, there's really not much heat being transferred, and there's fresh, cool air coming in here, being heated and blasting out here. Good. So that is referred to as the second mechanism And you know, we'll always put our cartoon up here, TH, to remind ourselves that you're going from an area of higher to an area of lower temperature heat transfer. So the second mechanism is called convection. Convection, write that correctly, T-I-O-N, and that is heat transfer by a fluid flow. So you can have it in air, you can have it in water as well. So heat transfer by fluid flow. Fluid flow. And the example I'll talk about is again the candle. So this time you've got your candle here. You got your flame, give it a little color just for fun. Okay. So we have a candle, and if you've ever had a candle burning and you snuff it out, you then see, after you snuff it out, some smoke rising up there. And we talked about it in terms of laminar flows and turbulent flows. You've seen that smoke rise up, and that's actually showing you the air current. Showing you the air current that was there before you snuffed it out. Okay, before you snuffed it out, there was also an air current. After you snuffed it out, some of the soot from the candle is then going to rise up in that very same air current, and of course we know it then dissipates up there. So heat convection by fluid flow, and a lot of heat can be transferred by a fluid flow, a lot more than by pure conduction typically. Okay. So good, you've got heat transfer by convection, which is the fluid flow. The third one, oh, and in terms of the, some more examples, all of your wind and weather examples are ultimately heat transfer by convection. The Earth is unevenly heated, okay? And locally and overall it's unevenly heated, and therefore there are always going to be convection currents that we call wind on all scales and all locations. Okay, so good, heat transfer by convection. The third one is these objects here that I brought along. So I'm going to do the demonstration first. Wish me luck. The idea is to ignite the matches over here by turning on a really bright light here. And the heat, of course the light's very hot and bright, but the heat is apparently traversing space here, and it does not need any air in between. And we're just going to reflect it here and focus it on those matches. Okay. That's what I'm claiming at any rate. So here's the bright light. And flame should be there in a moment. There we go. We have ignition. Okay. So we ignited those matches across the distance of the table. Now, if this were the sun, we'd be warming ourselves here on Earth across 100 million miles of space. So, good, that'll go out. So yeah, what type of heat transfer is this? The point is we got the heat from over here to over here. It is heat transfer by radiation. So the third one is electromagnetic radiation. Actually talk more about that in physics 2B. Turns out that visible light is electromagnetic radiation, and other wavelengths of radiation as well, radio waves, etc. So from the point of this class, it's just visible light, and also not non-visible light, so I'm just going to say light very generally. And just to explain this demonstration, we have a parabolic reflector Parabolic reflector. And we have a very bright light bulb right here. And we put the light bulb in the focal point. And it's kind of like the light in your headlights of your car. The light goes in every direction, but the light that strikes the reflector here all comes out parallel. So you'll be doing this in physics 2A when you do optics, 2B, sorry, when you do optics. And then over here we have another parabolic reflector, same as, see, they're on a stand. So this side has the light, give it some red here, and these lights rays hit this parabolic reflector and they're reflected towards the focal point. Here we have in the focal point, here we put the matches. So matches on this side, light bulb on this side. Light bulb. And enormously hot and very bright as well. But that traverses empty space if need be, and we have the matches on this side. So those are the three heat transfer mechanisms, and that's the only three: conduction, convection, and radiation. This can be very complicated to even attempt to calculate anything, and we're not going to, but it's very rich in phenomenology. So convection, you can look up some interesting examples of it. For the radiation, I do want to say a little bit more. There's some numbers involved. I'll look them up in the book though. So radiation, Stefan's law. And the fact is that any object emits radiation. Any object that's above 0 degrees can emit radiation just by virtue of it having a certain temperature. So suppose we have an object here. I'm just going to call this the object. And we'll choose a sphere, that's good. It will be radiating energy in every direction, spherically. And the power radiated depends on the surface area and a couple of other things. So I'm going to write down the formula and then we'll analyze it and discuss it a bit. And I should also say, just as well as it radiates, it can also absorb energy. So Stefan's law, let's go ahead and write both radiation, absorption. Okay. Both are possible. So how does this law look? Power radiated, we'll use the letter P, is equal to sigma E A T to the fourth. Let me get the number on one of these out here before we move on. So I'll write it in the order they have in the book. Sigma A E T to the fourth. So this is a natural constant, Stefan's constant, or the Stefan-Boltzmann constant, 5.6696. 5.6696 times 10 to the minus 8. Not going to do the units yet, right? This here is called the emissivity. You can almost think it's like a fudge factor because 0 less than or equal to E less than or equal to 1. However, for a black object, this is just 1. And so, yeah, we can often take it as 1. Emissivity. It has to do with how well an object absorbs and reflects. So a perfect reflector, a perfect mirror, would actually have 0 here for E, but a perfect black object that completely absorbs everything coming in would have a 1. Yeah. So. And then this is the temperature of the object in Kelvin. So T in Kelvin. Okay, so knowing those things is what we always want to do. What are the units of sigma? What are the units of sigma? This is a dimensionless number. This is watts. So it's going to be watts, and now just solve for sigma. Divide by A and T to the 4th. Watts per meter squared, Kelvin to the 4th. Watts per meter squared, Kelvin to the 4th. See what else we have here. And yeah, this is, did I say it? I should have said it. This is the surface area of our object. For example, if it were a sphere, it would be 4 pi r squared. Just giving it as an example. Area equals 4 pi radius squared for the sphere there. Okay, let's hold on to this formula for a moment. Now the interesting thing, and I mentioned it already, the radiation can be incoming and outgoing. So suppose we take a cold sphere, like a cold cannonball, okay, iron black sphere, and put it out in the hot sun. Then it's actually going to be absorbing power, namely it's going to be heating up. At some point it will reach its maximum temperature. You put something out in the sun, it doesn't just melt, right? Put it out in the hot sun, it reaches a maximum temperature, and at that point, since it has a constant temperature, it is radiating as much energy as it is absorbing. It's a kind of an equilibrium. And so the radiation and the absorption law are actually the same one with a different sign in front of them. So it's always radiating according to this law. Even say it's freezing, say it's 0 degrees Celsius. Well, remember these are Kelvin, so there's a big number there associated with it. But of course, the 4th power grows enormously fast when you increase the temperature. So yeah, we're going to want to do a couple problems of this. I'll assign out of the book if I find a good one. In particular, you could do an example. Say you have an old incandescent bulb, which isn't as light bulb, which isn't as common anymore, but of course they still exist. So you got a light bulb here, and it says 100 watts on it. Okay. So I'll just write 100 watts. It's radiating light, it's radiating heat. So what's the relation of this light bulb to this law right here? Okay. Now we're radiated. We could look at it in 2 different ways. We could start with the filament. So inside here there's a little filament. It's very thin, it's made out of tungsten. So this filament has a very small surface area, okay? Very tiny thing. This is a natural constant, and the temperature here is, and we're just going to take E equals 1 for any of these examples, okay? E here equals 1, done with it. But the temperature is going to be very high. In Kelvin or in Celsius, of that little filament. Okay. In fact, normal metals would just melt. Tungsten has a very high melting temperature. You could also say we have a light bulb, and we're thinking about the radiation from the surface area of the light bulb. Okay. okay? Then that area would be much, much larger. Temperature of the surface of the bulb, it may be too hot for you to hold in your hand, but it's not that hot, okay? So those would be the same wattage, 100 watts, different surface areas of the emitter would correspond to different temperatures of the bulb. So, yeah, interesting, very interesting formula. Okay, I'm going to consult the clock here. Good. I'm going to leave it at that. Let's see if we have a decent homework problem for you guys. We are in chapter 11, and we did a calorimetry problem. Those are important. And energy transfer problems. So this, just name the homework after the number here. So, homework 9, chapter 11. Let's see what's good here. Oh, some good ones here. Let's do 43. This one you'll find interesting because we're talking about the energy transfer by conduction from the surface to the bottom of a pond. Okay, so you'll need the transfer on the conductivity of water. You got temperature differences. Very nice, very basic. Let's see if we have one. I'm surprised here. '71 is very good. So 71, we're going to apply this law to the sun, and they'll give you the relevant data to talk about the power radiated by the sun. Which reminds me, there are other discussions of the power radiated by the sun. I'll get to those sometime. So that's a good one. What do we say? 71. 71. I did want to find was one with that. Yes. Okay. And 54 is talking about the filament of the light bulb. They, instead of 100 watts, they say 75 watts, okay. So good, these three are pretty basic, but you want to know them. And with that, we'll leave it and see you guys next time.